In this series, we will look at solving a problem through eras of home computer programming. The first version will be for the base Apple II, and this video will be going over the development environment, not writing the program. I want to show the programming process at the time in these videos, not just finished code. You can follow along with MAME. Don't want to use the command line version of MAME, so go download MAME UI. You will also need Apple II hardware ROMs. These are their names. I'm sure you can find them on the hard drive you backed up all your retro computing stuff to. Just do a search for all these file names together on your hard drive. After you've found those lost files, put them in the ROM directory for MAME UI. Move the zip files themselves. Do not unzip them. Launch MAME UI and search for the Apple II platform. Note, the 2 in Apple II needs to be brackets, not capital I's. Right-click on Apple II in the list and select Properties. On the Display tab, check to run in windowed mode. On the Miscellaneous tab, check Show Menu. I also go to the Sound tab and change the sound mode to none because I dislike beeping. Just double-click on the Apple II entry on the list to start it. Is it broken? Why is the screen filled with garbage? This is actually normal. The Apple II doesn't set the screen to blank on startup. We do have a nice blinking cursor though. Let's see what the system can do. Help. Man. No. The Apple II has no built-in help. The system is too limited to spend resources on anything other than functionality. Similar to old video games, not having in-game tutorials and explanations of controls, you need to look at a physical manual because there is not enough space to explain the system to you. I mean, in the modern environment, everything's such a mess you have to constantly look stuff up on Stack Overflow, so maybe it's not so different after all. The Apple II arguably doesn't have an operating system built in. It has a few programs in the system ROM. The initial console you boot to is called the Monitor program. The Monitor program is just a thin wrapper around the hardware. It mostly has tools for manipulating the system's extremely limited memory. You could even accidentally modify RAM being used by the system monitor. Any programs you run will have unrestricted access to the system as well. There are no processes, users, permissions, floppy drives on the original model, and no hard drives. It can save data to a cassette tape though, so that's cool. Or something in the vicinity of it. Let's take a look at these memory manipulation tools, because in order to do any development on this system, you're really going to need to know how to use them. This will also give you a good introduction to how the simple console on the Apple II works in general. We can view the content of memory at an address by just typing an address and then pressing enter. We can view a range of memory by giving 2 addresses separated by a period. You can enter data into memory by giving an address, a colon, and then the data you want to be entered from that point onward. You can read that data out and see the change. One thing to note is the Apple II keyboard layout is different from a modern keyboard, and MAME tries to simulate this. And that means that to enter a colon, you actually need to press the dash key, which is to the right of 0. You can enter data at the last place you started entering or viewing data from by just typing a colon with no leading address. Then you can check to see what that memory change looks like. See how it's from the starting address, not from the ending address that we used previously, starting at 800 here. The Apple II uses a 6502 CPU, and you can view the registers with a special command. If you press Ctrl-E, basically a invisible character is entered on the command line. And then if you press enter after that, it will print out the registers to you. There's a special case for the colon letting you enter data at the area you just viewed related to viewing the registers. If you do Control-E to look at the registers and then do a colon, you can provide 5 numbers and those will be loaded into the 6502's registers in the order that they're printed out by the Control-E command. Let's go back to looking at memory. If you press enter without a command, it will show you the bytes up to the next 8-byte boundary in memory from wherever you had left off. If the last address inspected isn't on an 8-byte boundary, you will see the bytes that would lead up to that boundary. You can move memory, really just copy it since it's not cleared away at the original location, by typing the starting address where you want to copy to, then doing a less than sign, then a range of data you want to copy, and then ending with an M for move. This has some broken behavior if your destination is within the range you're copying. So say you had 10 bytes you wanted to shift down, and you wanted to shift them down by 5, so the new starting point is right in the middle of the current location of that data block. That's not going to work right. But you can work around that by just copying the data block somewhere else first, and then copying it from there to wherever you want it to start. The mechanics of the console are very primitive. There's no space for any kind of command history, so pressing up will not get you the last command you entered. And there's also no normal backspace. Instead, the position of the cursor controls how much of the command is actually going to be run. So if you want to backspace, you just move the cursor left to the point that you wanted the command to stop, and then you could press enter there. See how I moved the cursor to the left past those last 2 4s, and then when I press enter, it shows that only the first 2 4s were actually part of the command that was run, and you can verify in memory that only 2 4s were entered. This also means that if you want to modify a command, you have to remember to move the cursor all the way back to the right again, so the full thing will actually execute after you moved it to the left and overwrote whatever characters you needed to change. If you press escape and then E, that will clear everything in the command to the right of the cursor. And I do mean press escape and then E, not hold escape and with it held down press E. You can use Control X to get a new line, pressing and releasing escape, and then doing Shift P, which is where the @ symbol is on an Apple II keyboard, will clear the whole screen for you. Then you could just press left once or press enter to get a new line. Another useful thing to know is a soft reset does not clear memory other than some values used by the system monitor. So if you crash or hang the machine, you can just do a soft reset to get it unstuck and you won't lose what you've done in memory. With the OS, if we want to call it that, covered, let's do some basic coding and debugging. We could just use the system monitor. Since we can write values to memory, we could write out our program on paper, translate it into machine code, and then enter the machine code hex values into memory with the system monitor tools. On a system just slightly more primitive than the Apple II, this is what people would have had to do. Fortunately, we aren't quite that bare bones, though only just barely. We can write assembly programs rather than writing machine code directly. This assembly will be written with the built-in assembler, the mini assembler. The manual tells you this program is stored at address F666. Anyway, To run code at an address in the monitor, you provide the address and add a G at the end, and then just press enter. I believe the G is just short for go, or go to. The Apple II doesn't support lowercase letters, so you do not need to hold shift to capitalize F and G in this command. Oh look, the cursor changed. We're now in the mini assembler. What did you expect? A text editor? Nope. It's called a mini assembler for a reason. To start assembling, you type an address, a semicolon, and then an assembly instruction mnemonic. The mini assembler immediately assembles the instruction to the address when you press enter. This particular instruction loads, that's what the LD is short for, 0 into 6502's A register. The pound sign next to the zeros tells the assembler to treat that 0 as an immediate value or a constant value, rather than seeing the 0 as an address, which would mean to go read whatever value was at address 0. As long as you want instructions in sequence, you do not have to give an address after starting. Each new instruction will be assembled into memory right after the last one. You do need to start the line with a space though. This next instruction stores, this is what ST is short for, the content of the A register in memory at address hex 50. The mini assembler always assumes a number is in hexadecimal. RTS is short for return from subroutine. This tells the 6502 to jump back to whatever called this section of code. If we don't include this instruction, the CPU would keep trying to sequentially execute memory, which is most likely going to be garbage values that will cause the machine to hang. After writing code, probably the first instinct is to run it. Before that though, we should ask ourselves what our expected result is. We expect this to set data at address 50 to 0. We should really check if address 50 already has a value of 0, and if it does, change it to something else before we run the code so we can actually know it worked. Monitor commands can be run from the mini assembler by starting with a $sign and then entering the monitor command. So we can do $50 and see that address 50 is 0 right now, so then we should set it to 1. Now we can run the program. We can verify the result, looking at address 50, and see that it is now set to 0. Especially early on, I do not advise writing a ton of code at once. It tends to lead to frustration and confusion. Build up what you need by coding bit by bit, thinking carefully about expectations, set up the system so you'll be able to validate, run the code, and then check for what you expect. You can still get into problems when your code does do the things you expected, but has other accidental effects you didn't notice. Despite that, in my experience, this method of slowly building up is way less frustrating and more satisfying than coding a ton and hoping it works. When you're inexperienced in particular, you possibly don't quite understand how the instructions actually work, and if you try to code everything at once, if you're mistaken in your understanding, you're going to end up needing to rework your whole program because you wrote it on an incorrect notion. On that theme, it would be good to validate some of the inner workings of our code to make sure we didn't get our expected result by accident, but actually got it the way we thought we did. Basically, double checking our understanding of everything so far. It would be nice to see the registers data, but using Control-E doesn't really work because after returning from our subroutine, the system code uses the registers, so it won't have the values from our program in them. But we can use the trace and step commands to see the registers. To trace, you do basically the same thing you would to run the program, but instead of using a G, you use a T. This will run every instruction and print the register state after each instruction is executed. Notice we can see some parts of the system code we are returning to executing, and they modify registers, which is why Control-E won't work. Also, doing a trace messes up where the mini-assembler will implicitly assemble to next, so you'll want to give an address in the mini-assembler after doing this. Stepping is very similar. You use a S instead of a T, and it will let us step through the code. We just have to have an S by itself each time we want to step. You can also do a kind of breakpoint with the BRK break instruction. Another quick tip for using the emulator: you can paste in commands you have prepared in something like Notepad. So I'm gonna do that because I have some assembly I want to enter quickly. When you modify an existing program, you'll want to use the L command to disassemble the memory so you can see the whole program and check your work. L is short for list, I believe, since it was common to refer to source code of a program as its listing back in the day. With that put in, say you want to break at the instruction at 804, make a note of that address and the data that's there, so 804 and 85 in this case. Then you can assemble a BRK instruction to that location, and it's a single byte instruction. So if you have it overwrite a 2-byte instruction, which is what we had there, the disassembler view will be confused from that point on because it just looks like gobbledygook because there's a break followed by something that doesn't make any sense that's a byte. But now if you run the program again, it will run until you hit the break instruction. You can look at memory, you can modify registers in memory. When you want to resume, just set the memory where you put the break instruction back to its original data, and then use G to resume from that address. And we can see that the 51 was set to 20 because we changed the register when we broke into the program before we went back and executed the store A in 51. Obviously, this is not the most convenient system, but it is the fundamentals for how debuggers work even today. They just have a bunch of code to manage setting and unsetting breakpoints so that they don't get totally deleted like we did right here. Couple final notes. Sometimes it's handy to use the break instruction instead of RTS just to avoid having the registers altered by returning from a subroutine. And when you're in the mini assembler, if you want to go back to the system monitor, it is at address FF65. That wraps it up for now. A rough introduction to the Apple II console and assembly environment. Hopefully it was interesting. I tried to give enough information so that if you got stuck or made mistakes, you could recover and experiment. If you want to know more, there's plenty of documentation on the 6502 CPU the Apple II uses, and the Apple II specifically, online. This should be enough to get you started. In the next video, we will actually code a program now that I've gotten all the foundations out of the way so I don't have to constantly get distracted explaining some new minor thing. Don't know how many people are actually interested in explorations of historical development environments, but we shall see, I guess.